So let's get into a little bit of statistics today. It's going to be kind of a blitz at you here, trying to get through some of this stuff and show you some of it before our end of course, which is Wednesday, barring any inclement weather type things. So I guess this is lesson 36. Yeah, give me just a second. So what we're going to start with and spend most of the day with is sequences and series, and talk about those sort of things. So we'll give that. You guys will be in 124. Stacy will be in ring 124. It's not 124 is junior high hallway, I think that's right. All right. So when we're dealing with sequences and series, sequences is where we start with. There's different formulas that come up. A sequence is just a list of numbers. You've been doing that since elementary school. When you're on TCAP, they give you like 3 numbers and you have to find the next 3, that sort of thing. That was a sequence that you were finding the next terms to. Well, as you progress a little further, you get into writing formulas for those sequences. And there's 2 different types of formulas that we'll deal with. One is called a recursive formula. And with recursive formulas, what that means is you're going to have information about the previous terms. Recursive, you have to have information about the previous terms. So you have to have either the very first term or the 2 previous terms, depending on what the formula requires. And then the better formula is what's called the explicit formula. And it's where you can find any term in a sequence. They'll tell you which one, like the N is like 31st term. You plug a 31 into the formula and it gives you the 31st term of that. You plug a 1 into the formula, it gives you the very first term. You plug 172 in there, it gives you 172nd term of the sequence. So the explicit formula is a really good one. And the reason I spend a little bit of time talking about that is because on EOC, a lot of times they will ask, which one of these would be a recursive formula for this sequence? And it'll have a sequence there, and they're looking for the recursive formula. And the recursive formula, you've got to keep in mind, has to have information about previous terms. If you'll remember that. And one of the things that I kind of think of that recursive and reverse kind of sound the same. And if you think about previous terms, that's like thinking reverse. So recursive has previous terms in it. Explicit formulas, they might give you a sequence and say, what's an explicit formula for this sequence? And the explicit formula, you don't have previous terms in it. You have just an N in there. There's no previous terms information in there. So let's look at a few of these and try to build up to this. And this is not my normal way of teaching. You guys know that I usually do a little bit better job of this. But we're trying to blitz through some things and get you some information that you'll catch a little bit of. So hopefully give you enough idea to get started on some of the problems that you're going to might encounter on the EOC. I don't know how much of this will be on there, how much won't be. But I'm just trying to cover as much of it as I can today and tomorrow. So the first one, it gives us a sub 1. All that means is that's the first term of the sequence. A sub n is the sequence term. When you go above that, that'd be a sub n plus 1. The next one would be a sub n plus 2. If you go to previous terms, that's a sub n minus 1, a sub n minus 2, a sub n minus 3, and so on. It keeps going both directions. So the subscript just talks about what term you're dealing with. So a sub 1 is the very first term in the sequence. And then you look at the formula on number 1 there, and it says 1 minus 2a sub n minus 1. So to find the second term for that problem, a sub 2 would be 1 minus 2 times whatever a sub 1 was. A sub 1 was 4. So we plug that in, And we get the second term in this sequence would be 1 minus 8, which would be negative 7. So we're looking for 6 terms. So the first one's 4. The second one's negative 7. Let's find the next one. You would do 1 minus 2 times the previous term, which would be negative 7. So 1 minus 2 times negative 7. 2 times negative 2 times negative 7 is positive 14. 1 plus 14 would be 15. So the third term would be 15. The fourth term, you're going to use 15 to find it because it's a recursive formula. You're always just plugging in the previous term. So 1 minus 2 times 15. So 1 minus 30 would be negative 29. Do what now? I plugged in 4. 1 minus 2 times 4. Plugged in the first term. You're always, if you got a formula, and it's a recursive formula, they're always going to have to at least give you the first term of the sequence so that you can do anything, or give you a term in the sequence. They can't just give you the formula and go. If it's an explicit formula, yeah, they can just give you the formula and say, find the terms. You don't have to have anything else. Next term, we plug in the negative 29 in here. So it'd be 1 minus 58. 1 plus 58, which would be 59, because it's double negative there. And then plug in that for the sixth term. The sixth term, 1 minus 2 times 59, be negative 117. And we found all the first 6 terms in the sequence. So recursive formula because it had a previous term in there. Look at number 2. It's a little tougher formula. More stuff going on. They give us the first 2 terms of the sequence. A sub 1 is 2. A sub 2 is 3. And then they ask us to use this formula to find the next 4 terms for this. So we'll just we'll get started with it, and then you could continue if you want to. So to find the third term, you're going to plug in a sub n minus 1. Which one of these, 2 or 3, is the previous term, a sub n minus 1? We're trying to find the third term. The a sub n minus 1 would be the second term. So the second term is the 3, and then a sub n minus 2 would be the 2. So when you plug that in, it's 3 to the third power minus 2 to the second power. You got to be careful on that formula there. So it's 3 cubed minus 2 squared. 3 cubed minus 2 squared. So that'd be 27 minus 4. Should be 23. And then to get the next term, you would use 23 in the front. So you cube 23. I don't know that. So 23 cubed minus 3 squared this time. It gets big pretty quick here. 12,158. The next 2 get into scientific notation because the numbers are so large, because you're gonna cube 12,158, which we know is a really large number. The idea here though is concept. A sub n minus 1 is the very previous term. A sub n minus 2 is 2 terms back. If it had a sub n minus 3, you'd have to go 3 terms back. That idea. Okay. So really easy concept. Notation wise makes it kind of tough because of the sub n minus 1s and sub n minus 2s makes those tough. Those 2 are recursive formulas because they have previous term stuff in them. When you look at number 3, it is a explicit formula because it only has the n in there. So to find the first term, you plug a 1 in for n. Find the second term, plug a 2, 3, 4, up to 6. So your terms are much easier to find. So 1 plugged in would be 6, 2 plugged in would be 11, 3 plugged in would be 16, 4 plugged in would be 21, 5 plugged in would be 26, 6 plugged in would be 31, and you got all the 6 terms. Much easier. Explicit formulas are lots better. We like those so much more. Number 4 is also an explicit formula, even though the exponent has the n-1 thing. It looks kind of suspicious, but the thing is that n-1 is the exponent. So when we plug that in, when we plug a 1 in to find our 6 terms, plug a 1 in, 1 minus 1 would be 0. 4 to the 0 power is 1. 1 times 5 over 2 is just 5 over 2. And then plug in a 2. 4 to the first power times 5 over 2 would be 20 over 2, which is 10. Plug in a 3. 4 squared is 16. Half of 16 is 8 times 5 is 40. Plug in a 4. 4 to the third is 64. Half of 64 is 32 times 5 would be 160. And then plug a 5 in. 4 to the fourth power would be 64 times 4, which is 256. 256 times 5 over 2 would be 128 times 5, which would be 640. And then the last one, plug a 6 in. 6 minus 1 is 5. So 4 to the 5th power, getting to where I don't know them now. 4 to the 5th power times 5 over 2. 2560 for the 6th term there. So explicit formula is so much better and easier to do. Just plug in the numbers that you need for whatever term out of that. So number 4 is another explicit formula because you don't need any previous term information. And these are going to be fractions probably. Plug in a 1, that'd be negative 3 over 6, which would be negative 2 over 6, which would be negative 1/3. Plug in a 2. 2 minus 3 is negative 1 over 7. Plug in a 3. 0 over 8, which is 0. Plug in a 4. 4 minus 3 is 1 over 9. Plug in a 5. 5 minus 3 is 2 over 5 plus 5 is 10. So 2 over 10 reduces to be 1/5. And then the last one, plug in a 6. 6 minus 3 for the top be 3. 6 plus 5 on the bottom is 11. So that's 3 11s. So they give you the formula, want you to find certain terms to it. You just plug in the numbers. If it's an explicit formula, you plug in the numbers 1 through wherever they need you to go to. If it's recursive, you got to use the previous term to get the next one. Number 6, kind of review a little bit with square roots. That's again an explicit formula. And then last one. Plug in a 1. 1 plus 7 is 8. How does the square root of 8 simplify? 2 radical 2, good. Plug in a 2. Square root of 9 is 3. Plug in a 3. It's the square root of 10, which doesn't reduce. And then plug in a 4. Square root of 11, which definitely doesn't reduce. Plug in a 5. The square root of 12, which reduces to be what? Flip it around. 2 square root of 3. This is pair of 2s, not pair of 3s. And then the last one, plug in a 6, be the square root of 13. So taking us and finding the next terms out of that is kind of what that little part's focused on. So being able to extend a sequence and all that stuff. Okay. All right. Next, let's talk about what makes something an arithmetic sequence versus a geometric sequence. So arithmetic sequences add every time. Can't turn on the air. All right, so arithmetic sequences add, and that addition is what we call the common difference. Okay, so addition, arithmetic goes together. Addition of a common difference. And there's a formula for writing an explicit formula for an arithmetic sequence. That formula is a sub n equals the common difference, we'll use D for difference, times n minus 1 plus a sub 1. We've got to have the first term, but we don't have, this is not a recursive formula because we don't have to have the previous term to get the next one. So we'll call it an explicit formula. So we're going to work on writing some of those. A geometric sequence multiplies by what's called a common ratio. And the way the formula works for a geometric sequence is you're going to take the first term and we're going to multiply it times that common ratio, r, to the n minus 1 power. We're going to kind of put this to work a little bit here. Now, the reason we need to know those formulas is that it isn't incredibly efficient to take an arithmetic sequence that adds 3 every time, and if they ask you to find the 50th term of that sequence, to write it out till you get to the 50th term, that just doesn't make sense. There's got to be a better way, and that formula is going to be the better way. Geometrically, it's same idea. It doesn't make a lot of sense to write out each individual term until you get to the one that they want. And that also introduces a ton of places where you can make a mistake. But if we can memorize those formulas there and know when they're used, that can help us in being able to find a certain term in a sequence, which is what this next little set of problems is talking about. So number 7, the instructions say determine if the sequence is arithmetic or geometric. So we're going to look at, does it have a common difference? Do they add the same thing every time? Or do they multiply by the same thing every time? And then based on that, we're going to write the formula for that sequence and then find the indicated term. So the first one's asking for a sub 51. It's a 51st term. It doesn't make a whole lot of sense to write out 51 terms to find that value. Yeah, it could be done if you don't know how to do it any other way. You could do it that way, but it would take you a lot longer than the way that I'm going to show you. Okay, so let's look at this problem and try to see if it's arithmetic or geometric. So how do you get from -12 to a -5? Add 7. If I add 7 to -5, do I get to 2? Yes. Do I get to 9 from there? So I'm adding 7 every time. So they're adding the same thing each time. So that tells me that this is arithmetic. Okay, so this is arithmetic. So we've determined that that's the case because they're adding the same thing every time. Now I want to write that formula using this thing up here. It's arithmetic. I'm going to use that formula up there. Okay. So a sub n equals the common difference. How much we adding every time? Positive 7. N minus 1 plus the first term. What's the first term in that sequence? -12. So that's what's going to go there. Now I have a formula for finding any term I want to. I want the 51st term, so I'm finding a sub 51. So what do I put in the place of n? 51. And work that out. 7 parentheses 51 minus 1 plus negative 12. 338. The 51st term. Yes. If we needed the 164th term, we could plug in 164 for n and get that answer instead of writing out the sequence that far. Okay, all based on building that formula. If it's arithmetic, it's always going to be common difference times n minus 1. That never changes, plus the first term in the sequence. Okay, let's look at number 8. How do we get from a 3 to a negative 6? If I multiply by negative 2, that gets me there. What about from negative 6 to positive 12? Do I multiply by negative 2 again? Yes. So that's happening every time I'm multiplying by negative 2. Right, really small. So that is my common ratio. So this is geometric, and I'll just abbreviate it geo there. Geometric with a common ratio of negative 2. So we're going to write the formula. A sub n equals, the formula says the first term in the sequence. What's the first term in this sequence? 3. So there's the 3 times the common ratio, negative 2. And I'm putting it in parentheses because I'm going to use a calculator to do this in just a second. So I need it in parentheses so it doesn't screw up the negative sign, to the n minus 1 power. That is the formula for this sequence. I can plug in any n value and find that term. If I wanted the second term, if I plug a 2 in right here, that's going to be 3 times negative 2 to the first power, which is 1. So that'd be 3 times negative 2 to the first power, which is 3 times negative 2, which is negative 6. So it works. You can check your formulas to see if they get you the next term. And then we want to find the 14th term in this one. So a sub 14. 3 times negative 2 to the 14 minus 1. And I'm going to use a calculator to help me. Parentheses, negative 2 raised to the 14 minus 1. I probably should have just did 13 there, but it's okay. Negative 24,576. So geometric sequence because it multiplied by the same thing each time. Let's look at number 9, a little tougher one. 3,125, 2,500, 2,000, 1,600, and so on. Well, to get from 3,125 to 2,500, that'd be subtracting about 1,600 or about 625. And I know that ain't how you get from here to here. So that rules out arithmetic. Let's hope it's geometric. If it's not either of those, then we got to think about something else. But I'm pretty sure it's geometric now. So how do we find out what we multiply by to get from 3,125 to 2,500? Divide. If I divide 2,500 by 3,125, and then do the next pair, 2,000 by 2,500, I should get the same ratio. Common ratio, fractions, goes together. So 2,500 divided by 3,125, 0.8, 25, or 2,000 divided by 2,500, 0.8. It's the same. So my common ratio is going to be 4/5. That's the fraction for the decimal 0.8. Okay, so that's our common ratio. Geometric R is equal to 4/5. So when we write the formula, first term is 3125. Common ratio is 4/5 to the n minus 1. We want to find it says a sub 9. So all we're going to do is plug a 9 in to that formula. Bless you. And work that out. 3125 times parentheses 4/5 raised to the 9 minus 1 is 8. So I'm just going to put that in there. And I'm going to change that to a fraction. 65,536 over 125. That would be the 9th term in that sequence. It's geometric because we had to multiply by something to get to the next term. Let's look at number 10. It looks a little weird because it's got fractions mixed together with integers, but the idea is still the same. How do I get from -2 to -7/2? Well, I add a -3/2. That's good. So that means this is arithmetic with a common difference of -3/2. -7/2 is also -3.5. So if you think about it in decimals, that might help you see the pattern a little quicker. Let's think better in decimals. Since that's a terminating decimal, you could do that. Let's write the formula. Common difference times n minus 1 plus the first term. Always going to be that way. Doesn't change. Okay. Then we're finding the 26th term of that sequence. So a sub 26 and work that out. So -3/2 times 25 minus 2. Math enter because it's in fraction form. -79/2. And I put it in fraction form because that's the way the original problem was. So arithmetic sequence, again, adding the same amount every single time to get to the next term. And then you're using that formula there. All right. Let's skip to 13. Get into the couple of word problems that deal with this. So, Sean bought a boat for $35,000. Each year, it loses 10% of its value. Write the equation that models the value of the boat, then find its approximate value after 15 years. Okay, so this is you got to think a little bit on this. Okay, so when we're looking at that value of the boat, we want our formula to be the value of the boat. It's losing 10% of its value each year. So the first year, it's going to lose 10% of what number? 35,000. The second year, is it going to lose the same amount? No, because the second year it's not worth 35,000 at the beginning of the year, is it? It's worth less than that. 20 be worth like 31,500. Like that, right? And then so you lose 10% of that. And then the third year, it's going to lose 10% of that new value. And then the fourth year, 10% of that new value. How much is it worth each successive year? I think on the, it's called the complement if you think about it in geometric terms. But What's the complement of 10%? If 10% is how much it's losing, how much you keeping? 90%. So our common ratio for value of the boat is 90%. So this is a geometric sequence in very good disguise in a word problem. So it really, the value of the boat is 35,000 times 0.90 to the n minus 1. That's the formula for a geometric sequence. The 0.9 is the value of the boat. It's how much it's worth each year. Okay? To find how much it's worth after 15 years, you just plug a 15 in for n. I'm going to round to the nearest cent since we're dealing with money. 35,000 times 0.9 raised to the 14th. $8,006.88. That is how much that boat is worth after 15 years. If it loses 10% of its value each year. A lot of companies use this. It's called exponential depreciation. Some companies use this. Most businesses use what's called straight line depreciation. You're losing the same amount of value each year. With exponential depreciation, the value you lose changes every year. So it makes it a little bit more difficult on the budget committee as far as setting up those sort of things. So straight line depreciation is most commonly used, but this exponential depreciation is how, when you're going to sell something, that's how it works. When you go Kelly Blue Book, a lot of you guys are looking for cars and stuff now because you ain't close to driving. A car's brand new, you drive it off that lot, it doesn't lose just 10% of its value. It loses a lot more percentage of it. But the next successive years, it doesn't lose quite as much value out of it. So it's quite a different formula for that. But it's more of an exponential depreciation than a linear depreciation. With that. So 14. Jack has burned 250 calories on the treadmill before switching to the elliptical at the gym. On the elliptical, he burns an average of 11.8 calories per minute. Write an equation to model the total number of calories burned and find how many calories he burns 25 minutes into the elliptical workout. That word right there is the most important one in that sentence. When we did word problems back August, September, when we saw per in there, what did that indicate for the problem? True. Kind of, but not really. What part of an equation would that indicate? 11.8 calories per minute. Think about it. It's a constant amount each time, right? So it's moving the same amount each time. Be like a slope. The time we saw per, that indicated slope. So slope is like an arithmetic sequence. It's that common difference. It's that common rate. So this is an arithmetic sequence with the common difference being 11.8 calories per minute, n minus 1. But when we start getting on the elliptical, how many calories have we already burned? 250. So our first term in the sequence is 250 because that's what we started with. Okay. So we're looking for, after 25 minutes, about how many calories have we burned? So 11.8 times 24 plus 250. 533.2. Write out calories there since we're dealing with a word problem out of it. So kind of mixing these things in. Do you have to know geometric and arithmetic sequence to be able to solve that problem? No. You guys are smart enough to kind of work around it and figure out what's going on, and you got a lot of different strategies that you could use to solve that word problem. But these kind of interrelate with the sequences that we were talking about there. All right, well, let's drop it into the next thing, which is taking a sequence and turning it into a series, okay? Now, a sequence is just a list of numbers, okay? So when we had a nice, easy sequence, something pretty simple, 3, 6, 9, 12, 15, that sort of thing. That's a sequence. You know what makes it a series? The plus signs between. That's the only difference. And you add it up. Okay? So a series is a sum of a sequence. That's what a series is. Okay? So when they say series, you got to think, oh, I'm adding. That's all I'm doing is adding. Taking a sequence and adding it up. Okay? So for number 15, they say, okay, here you have a sequence, and we want to treat it as a series and find S sub 7. That right there just means the sum of the first 7 terms. S sub whatever number. If they said S sub 3, it's the first 3 terms. S sub 7 is the first 7 terms. Add them up. S sub 28, add up the first 28 terms. That's all that means. Okay? So for this one, we've got the first term. We've got a formula that's what kind of formula is that? Is that recursive or explicit for 15? Because there may be some questions that's all you got to be able to answer. It's recursive. Why? Gives you the first term and then what's used in the formula. Yeah, a sub n minus 1. It's using a previous term to get the next term. So that's what makes it a recursive formula out of that. So we're going to find the first 7 terms. We have the first one. We know it is -4. We need to find the second, third, fourth, fifth, sixth, and 7th. And then we're just going to add them all up. So to find the second term, we plug in -4 into our problem. So that's going to be 4 times -4, which is -16, plus 11. -16 plus 11. -16 plus 11. -5. Plug the -5 into the formula. 4 times -5 is -20, plus 11. -9. Plug -9 into the formula. 4 times -9, -36, plus 11, -25. Plug -25 into the formula. 4 times -25 is -100, plus 11, -89. Plug -89 into the formula. 4 times -89, the 320 plus 300. So -345 is the final. And then what's the last term? -1369 is what I got. Since it's a series, we just add all those up. That's what a series does, just adds them all up. So that'd be -18 and -25. Heck, I'm not doing that. -1846. Folks, whoever's phone is beeping or doing that little sound, turn it off. You don't have to get your text messages and all your Snapchats and stuff while we're doing class. You can turn your phone off, or at least make it shut up. Now, number 16, is that a recursive or an explicit formula? Why is it explicit and not recursive? Yeah, it doesn't give you a previous term, and there's not a previous term in the formula. Okay, there's not an a sub n minus whatever in there. So find the first 7 terms. That just means plug 1 through 7 into that problem. I'm going to use my calculator to help me do that. I'm going to go to y equals, and I'm just going to type in x squared minus 8 into the y equals menu. And then I'm going to hit second graph. And now I'm going to type in 1, enter, 2, enter, 3, enter, 4, 5, 6, 7. That finds me the first 7 terms of that sequence. Because it's an explicit formula that I can do that. If it's a recursive formula, you can't do that. Explicit formulas, you can't. Because they're just equations. You plug in the x value and work it out. All right, so we got to add all that up. So 41 and 9 is 50. And 45 would be 95. Minus 11 would be 84. So you can use your calculator to help you generate the terms on an explicit formula. That really helps a lot. Okay. All right, I'm going to show you another calculator trick. This big weird looking thing here is what's called a summation. That Greek letter there is the sigma, capital sigma. If you have friends that are in fraternities, sororities, you'll see that letter in a lot of them. They use Greek letters there. So that's the Greek letter sigma. And what it is it's a summation of a certain term set from a series. So it's a series because it's a summation. This one, the first one, starts at 1, the first term, and goes through the 12th term. That's what that says. So the bottom number down here is where you're starting. The number up top is the last term you're getting to. This is the explicit formula for that sequence or series in this case, since you're adding it all up. So your calculator has a nice thing. If you've got a TI-84 Plus, you've rented one from us, or you got one of the color ones, you're going to be good to go on this. If you've got a TI-83, it won't do this, and you'll have to actually find each one of those individual terms and work it out and add them up. So if you don't have a calculator, what you've got to do is plug in a 1, work this out, get that number, write it down. Plug in a 2, work that out, write that down. Plug in a 3, and so on until you get to 12. And then add all those numbers up. With the calculator, you can hit the math button and go right there, press the up arrow, and you'll see an option called summation. And when you, well, I need to get in the regular calculator screen to do that. Math, summation. And then it asks you to type in all the stuff. Well, I got to pick a variable. I'm going to use X instead of N just because it's easier to type. I can just hit that 1 button beside alpha and get the X. And then you put a 1, press the right arrow key, put a 12 up top, plus right arrow key. And then here's where you've got to be careful. When you type that in, you need to type it in parentheses, X minus 2, close parentheses, raised to the 3rd. Put in the extra set of parentheses. Hit enter. It adds them up. It finds all of those terms and then adds them up all in one swoop. Okay. Well, it would be 3,024. It's the same idea. Just got a different formula. Okay, so I'm going to hit math, go to summation. Again, they're using K, but I'm going to use X. But this one doesn't start at the first term. It starts at the third term and goes to the 17th term. And then I'm typing in x squared minus 5x in there. And enter. 1030. But what that's doing is it's plugging in this number down here, working it out, getting the term, writing it down. Plugging in the next one, 4, work it out, get the term. 5, 6, 7, 8, 9, all the way to 17. And it adds all of those up in one little button press. So it's pretty nice use on the calculator. So that's for adding up a certain length of series. Okay. Now, and that's starting at any term. The next part on the next page, it says a sum of an arithmetic series, and then up the top it's got another box that says the sum of a geometric series. These are two formulas that we're going to use. All right, so the sum of an arithmetic series, that again, S sub n means the sum to whatever number of term you want to get to. So this is for starting at the first term and getting to a certain other term. It's going to be n times a sub 1 plus a sub n divided by 2. So it's going to take, if you want the sum of the first 12, it's 12 times the first term plus the 12th term divided by 2. And then if you want the 15th, first 15 terms, it'd be 15 times the first term plus the 15th term divided by 2. For a geometric series, the formula for adding together a certain number of terms is the first term times 1 minus r to the n over 1 minus r. R, again, is your common ratio. Remember, geometric, you're multiplying by a certain thing every time. So that R is that thing you're multiplying by to get there. All right, so let's look at a couple of examples of this using some series that are just written out. They don't have a formula for them. So number 19, we first need, or we need to decide, is this arithmetic or geometric? Because it depends which formula I'm going to use. So for number 19, is this arithmetic or geometric? Why is it arithmetic? Subtracting 3 every time, so it's a plus negative 3. They want us to sum the first 27 terms of that sequence or series. Do we have the 27th term? No. I've got to find the 27th term. So to find the 27th term, I've got to use that formula that I can write for an arithmetic sequence. So this ties it back to one of the other things we've done. So to find any term, I'm taking the common difference times n minus 1 plus the first term. So to find the 27th term, I'm working that out. Negative 3 times 26 plus 8. Negative 3 times 26 plus 8. So the 27th term is negative 70. So to find the sum of the first 27 terms of that sequence, I'm going to take 27 times the first term, 8, plus the 27th term, negative 70, all over 2. I'm going to use a calculator to help me out here. 27 parentheses 8 plus negative 70 divided by 2. negative 837. That's the sum of the first 27 terms of that sequence. That formula is somewhat important. And I want to think that that formula is actually given to you on your reference sheet for the end of course. We'll talk about it a little bit tomorrow. I'll look at it and let you guys, we'll talk about the reference sheet for that. All right, number 20. We got a series here. We want to find the sum of the first 7 terms. We've got the first 4 terms. So this one, it probably would make decent sense to go ahead and just find the next 3 and work it out. But we're going to try to work it with this formula here. But we need to find out how are they getting from one term to the next. So how are we getting from 60 to negative 30 and from negative 30 to 15? And from 15 to negative 7 over 2. Times 1/2. That's right. Well, not just 1/2, but we have to have the negative so it'll swap signs. So the R is negative 1/2. The great thing about geometric series are that you don't have to have a formula to find a certain term in it to do the sum. All you got to have is the R and what term you're going to sum to. So we're summing to the first 7 terms. So we're taking the first term, 60, times 1 minus negative 1/2 to the 7th power, all over 1 minus negative 1/2. So that's what I'm going to type into my calculator, is that ugly mess right there. So 60 parentheses 1 minus parentheses negative 1/2 raised to the 7th power. Getting that answer divided by 1 minus negative 1/2. I'm going to change it to a fraction because there's a fraction in the original problem. 645 over 16. If you went ahead and found the 5th, 6th, and 7th term to that geometric sequence just by multiplying negative 7 over 2 times negative 1/2, get that answer, multiply it by negative 1/2, and then did the addition with that, you get the exact same answer. That one probably wasn't much difference in doing it the long way or doing it this way with the formula. Okay. 21 and 22, it's another one of those summation things. That's a calculator deal. Put that in the calculator. Start it at 1, go to 27. There's your formula. It's all. It's nothing to it. This says X and M. That should be both of them should be an X there. It's a typo on my notes there. So I would go to the calculator. I'd hit math. Go to summation. X from 1 to 27, and then in the parentheses there it's 7x minus 19, and let it crank out the sum 2133. And that's what I would do for 21, 22, 23, and 24. Not very likely they're going to throw one of those at you that's too difficult or very long on the non-calculator portion of the test. They don't ask that kind of question. Again, this is a very broad overview of some of the statistics things. So 2133, what that is. And then you do the same thing for the next 3 problems. Let's drop down there to the word problem. 25 and 26. 25. Outdoor pavilion has 30 rows of seats. 20 seats are in the front row. And then it grows by 6 seats. Each row thereafter has 6 more seats. Using a formula, find the total number of seats at the pavilion. Okay? Is this geometric or arithmetic? Justify that. What's it take to be geometric? Okay, so for the first row, I got 20. How many seats are in the second row according to the directions there? It says there's 6 more in the next row. So that'd be 26. And then the third row would have how many? 32. Is there any, am I multiplying to get to the next one? No, I'm adding 6 every time. So this is an arithmetic sequence buried inside of a word problem. But the idea here is that we're going to add up the 30 rows of this thing using an arithmetic sequence. So if we can come up with a sum, we need to know how many, we need to know a sub 30. We know a sub 1 is 20. How do we find a sub 30? Well, what's the common difference? 6. Six times 29 plus 20. 194 is the 30th row, has 194 seats in it. A lot. Okay. Now, to find the sum of the whole pavilion, battery is dying. I'm going to take 30 times the first row plus the last row divided by 2. $3,210 seats. It's a pretty good size place. 26. May tell me how to say that name. That's what I was thinking. We'll say it. Katya. Katya. All right, Katya was hired at a company with a starting salary of $28,000. Is that a lot of money? No, not really. Each year thereafter, she receives a 1% raise. They really love her a lot. 1% is not much of a raise. Considering inflation is about 3%. So that really doesn't, you don't get ahead at all. So, but that's what's happening at this particular company. Hope she finds a new one soon. But she's going to stay there for 10 years. What is the total amount of money she will have earned after working 10 years? This is total amount, not how much is she making the 10th year. How much money she made in 10 years if the policy never changes and they just do a 1% raise each year. So is this geometric or arithmetic? Geometric because we're finding 1% of this year's salary, and then next year it'll be 1% of what you made that year, and so on. So we're multiplying by 1% every time. So our first term is 28 grand. Our common ratio is 1.01. Why am I using 1.01 and not just 0.01? That's right. So it's the original salary and the extra 1% that we're using there. Good job. All right. So since it's geometric, I can go straight to that formula for the sum of the 10 years. And that would be the first term, 28 grand, times 1 minus 1.01 to the 10th over 1 minus 1.01. And we just need to work that out. So I'm going to go calculator 28 grand times 1 minus 1.01 raised to the 10th. Oops. Do that. Parentheses in a different spot. And then I'm going to divide that by 1, parentheses, 1 minus 1.01. $290,941.95. This person is either a teacher or a social worker. Usually don't. That's the total amount of money she made, gross profit, or gross pay in 10 years. Yeah, that's not good. In 10 years, that's not good. So, but it is what it is. 28,000 is a lot more than a lot of people make around here. So, believe it or not. So, all right. Let's look at this last thing. It'll be the last thing we talk about today. Convergent and divergent geometric series. Okay. Divergent. What's that word even mean? Diverge. What is it? Y'all read that wrong? Yeah, there's it. Divergent. If something diverges, what direction does it go? Away. Right? Two roads divergent. The yellow roof is home. But divergent means it goes away. Okay? Convergent is the antonym of that. It means it does what? Comes together at one spot. Okay? So when we're talking about a geometric series, a divergent geometric series is going to spread apart. Each term is going to get further and further apart. That's what's happening. And it's not approaching one particular number. So a divergent series can be determined by looking at the absolute value of the common ratio. The common ratio, if you take the absolute value of it, if it's bigger than 1, the series is going to diverge because you're multiplying by something bigger than 1 each time. So it's expanding. The gap between terms is going to be expanding every time. A convergent series, it's less than 1 because we're multiplying by a smaller number each time. Each term gets smaller and it starts approaching a certain number. Okay. So let's look at a couple of these examples and decide if they're convergent or divergent. Okay. And then find the sum if possible. We can only find the sum of convergent series. That's that last thing there, right there. Highlight in yellow. Only convergent series have a sum. The sum of an infinite convergent series, a sub 1 over 1 minus r. That's the formula. That's not a certain number of terms. That's the entire series from beginning to infinity. It's an infinite series, infinite geometric series. The sum of an infinite geometric series. Okay, that only happens with convergent series. So let's look at each one of these and decide, is it convergent or divergent? So -1, -1/4, -1/16, -1/64. Are they multiplying by the same thing each time, and what are they multiplying by? They're multiplying by 1/4. -1 times 1/4 is -1/4. -1/4 times 1/4 is -1/16, and so on. So there's our common ratio. The absolute value of that is 1/4, right? Is that less than 1 or greater than 1? So it's convergent. Because the common ratio is less than 1. And then we find the sum of that by just plugging this into the formula. -1 over 1 minus 1/4. It is that easy. Negative 1 divided by 1 minus 0.25, which is 1/4. Negative 4/3. Excuse me. Sorry. Killing you guys in a heart attack. All right, so convergent series. That means, look how much of that was in the very first term. The very first term is negative 1. How much of negative 4/3 is that? A whole bunch of it. We're talking about this series going to infinity, an infinite number of terms. How big is 164? It's really, really little, right? Well, what would the next term be? What's 64 times 4? 256. All right. How big is 256? It's very small. I don't know if it's microscopic yet, but it's getting close, right? And we're not even very far into the sequence. So after we get past the 1/64, we're not adding very much at all. We're adding essentially 0 out of that. So the first couple of terms really get us close to the sum of the infinite geometric series there. Because it's convergent, those numbers are getting tinier and tinier as we go there, and it's adding 0 essentially at toward the end there. Let's look at 28 real quick. -7 to +14, +14 to -28, -28 to +56, and so on. What's our common ratio? -2. The absolute value of that is 2, so this one is divergent, which means there's no sum. Okay. Based on just what R is, you can decide if there's a sum or not. Okay. All right. This is where I got to with first block, so I'm going to stop at the same place for you guys. You guys got about 5 minutes or so left out of this.